In the eternal vacuum of darkness, a faint point of light travels along its predetermined path. The object this light represents has wandered the Milky Way for millions of years. It has witnessed the birth and death of stars, the formation and dissolution of planetary systems. Now it steadily approaches an ordinary yellow dwarf star system. That is our solar system. The story of this interstellar traveler begins on an ordinary night of observation. An observation site of the ATL-AS Automated Sky Survey System was executing its routine scanning mission as scheduled. This telescope system, located in Hawaii, was specifically designed to monitor near-Earth objects that could pose a threat to Earth. Its field of view covered vast swaths of the sky, automatically recording tens of thousands of moving celestial bodies each night. On that decisive night, the telescope captured a faint point of light with a brightness of only magnitude 25. This brightness equates to observing the faint glow of a candle from 1,000 kilometers away. In the initial automated classification, it was labeled as an ordinary asteroid in the outer solar system. This classification was based on its slow apparent motion and dim brightness characteristics. Initial orbital calculations utilized observations from the first 3 nights. Results indicated a typical trans-Neptune object, estimated to orbit approximately 5 billion kilometers from the Sun, beyond Neptune's orbit. Preliminary diameter estimates ranged between 2 and 8 kilometers, a size range common among small solar system bodies. However, as observational data accumulated through the 7th night, orbital calculation specialists began noting anomalies. The object's motion parameters did not match any known solar system orbital characteristics. Its orbital inclination was exceptionally large, nearly perpendicular to the ecliptic plane. This characteristic immediately alerted researchers. Further precise calculations revealed even more astonishing facts. The object's orbital eccentricity reached 1.2, significantly exceeding the hyperbolic orbit threshold of 1 in classical celestial mechanics. This value signifies sufficient velocity to escape the Sun's gravitational bondage. This is a visitor from interstellar space. The distinction between hyperbolic and elliptical orbits carries fundamental physical significance. Elliptical orbits indicate celestial bodies are bound within a star's gravitational field. They will perpetually orbit within this stellar system, unless disturbed by other celestial bodies. A hyperbolic orbit, however, signifies the body originated from infinite distance, and will return to infinite distance. It is merely a transient visitor within the star's gravitational field. This discovery immediately evokes two famous interstellar visitors in astronomical history. Oumuamua, discovered in 2017. This object is renowned for its extreme shape ratio. Its length is approximately 10 times its width, presenting an unprecedented cigar-like form. Its non-gravitational acceleration phenomenon continues to spark intense debate within the scientific community. Comet Borisov, discovered in 2019, exhibited more typical cometary characteristics, developing a distinct comb and tail, with chemical compositions closely resembling those of solar system comets, providing invaluable data for studying the composition of interstellar objects. The object now before us has been formally designated 3I Atlas by the International Astronomical Union. This naming follows systematic conventions. C denotes a non-periodic comet. 2025 indicates the year of discovery. None denotes it as the first such object discovered in the first half of July. The I in 3I specifically signifies its interstellar origin. The 3 indicates it is the third interstellar object discovered by humanity. This designation itself carries significant historical meaning. It marks humanity's establishment of an entirely new celestial classification system, dedicated to recording these visitors from other stellar systems. Each such discovery expands our understanding of cosmic structure and the distribution of matter, based on photometric measurements and thermal radiation models. Scientists estimate this interstellar visitor's chord diameter ranges from 0.6 to 5.6 kilometers. This size range holds significant implications. If it falls toward the larger end, it would be the largest interstellar object ever recorded, with a surface area capable of supporting complex surface features and geological activity. Its velocity is astonishing. reaching 58 kilometers per second. This speed far exceeds the orbital velocities of most objects within our solar system. Such high velocity can only be explained by intense gravitational interactions, likely occurring in its home galaxy, during a close encounter with a giant planet or the star itself. Throughout its lengthy interstellar journey, this object has been continuously bombarded by galactic cosmic rays. High-energy protons and other atomic nuclei strike its surface at near-light speeds, triggering complex nuclear reactions and chemical transformations. This process has formed a distinctive radiation-process layer on its surface, estimated to be up to 20 meters thick. This radiation-hardened layer acts like a time capsule, recording its history of wandering through the Milky Way. By analyzing the chemical composition of this surface layer, scientists can infer its exposure time in the interstellar medium and the radiation environments it encountered. When this interstellar visitor entered the inner solar system, scientists began observing a series of anomalous phenomena. Most striking was its brightness variation pattern, which began showing signs of cometary activity. It began exhibiting signs of cometary activity far earlier than theoretical predictions. Its light curve displayed irregular characteristics, sometimes brightening by 2 magnitudes within hours, before rapidly returning to its original state. Such rapid luminosity changes defy explanation by simple ice sublimation models, possibly hinting at a unique distribution of volatile substances on its surface. Another perplexing feature lies in the geometry of its orbit. Its flight path appears meticulously chosen at an optimal angle to the ecliptic plane, ensuring ample observation time, while avoiding close encounters with major planets. This coincidence prompted deep reflection among scientists. In early observations, it exhibited unusually low gas emission levels. Most comets at similar distances display distinct water vapor spectral features, yet this object only began showing clear gas emission lines when it reached 3 AU from the Sun. These anomalies caught the attention of Professor Avie Loeb, chair of Harvard's Department of Astronomy. As an innovatively minded scientist, Professor Loeb is renowned for challenging conventional wisdom. He systematically analyzed all available observational data and posed a thought-provoking question. Professor Loeb emphasized he was not claiming to have discovered extraterrestrial civilizations, but advocating for a thoroughly scientific approach to exploring all possibilities. Throughout the history of scientific exploration, many groundbreaking discoveries have emerged from the deep investigation of anomalous phenomena. His argument rests on multiple observational anomalies, including an unusually early onset of activity, irregular variations in luminosity, and distinctive gas emission patterns. Together, these characteristics constitute a compelling case warranting further investigation. Professor Loeb possesses a formidable academic pedigree, having served as chair of Harvard's astronomy department for a decade and published hundreds of highly influential research papers. These accomplishments lent his perspective additional weight. However, the scientific mainstream maintains a cautious stance toward his hypothesis. Many astronomers emphasize that in the absence of direct evidence, natural explanations should be prioritized. This principle, known as Occam's razor, is central to scientific methodology. Observations from the Hubble Space Telescope provide crucial evidence, demonstrating this object possesses a classic cometary structure, a cloud of gas and dust uniformly enveloping its nucleus. This is a clear indicator of cometary activity. There are no signs of artificial structures. Ultraviolet spectral observations from the Swift satellite detected distinct water vapor spectral lines. The intensity and profile of these lines highly match characteristics observed in solar system comets, confirming this object contains substantial water ice. A combination of orbiters around Mars provided crucial close-range observational data. The European Space Agency's Mars Express captured high-resolution images from 10 million kilometers away, revealing a completely natural cometary morphology. Detailed spectral analysis revealed a rich chemical composition, including water ice, carbon dioxide, carbon monoxide, and trace amounts of methane and ammonia. The proportions of these components exhibit subtle differences from solar system comets, reflecting the uniqueness of its formation environment. Particularly noteworthy is the detection of hydrogen cyanide molecules. This molecule, common in both interstellar media and comets, is a key component of prebiotic chemistry. Its abundance provides clues for studying the chemical environments of other stellar systems. Interstellar comets act as cosmic archaeological samples, preserving primordial information about their parent star systems. By analyzing their chemical compositions, we can infer the conditions and history of their origin star systems. This holds significant implications for understanding the universality of planetary system formation. As this interstellar visitor continued its journey into the inner solar system, new astonishing phenomena began to emerge. The Mir K-80 radio telescope array in South Africa detected radio emissions at specific frequencies emanating from the object. This discovery immediately sparked public sensation. Many speculated it might signify the detection of an extraterrestrial signal. However, professional astronomers soon provided a rational explanation. These signals corresponded to the natural radiation of hydroxyl molecules. Hydroxyl molecules are byproducts, formed when water molecules break down under solar ultraviolet radiation. They emit intense natural microwave radiation at frequencies of 1665 and 1667 MHz. This phenomenon, known as microwave maser emission in comet studies, almost simultaneously, astronomical observers worldwide reported significant color changes in the object. It gradually shifted from its initial pale red hue to emerald green and subsequently exhibited deep blue tones. Color changes are not uncommon in comets, but such rapid and extreme transformations are indeed extraordinary. Red is typically attributed to complex organic molecules on the surface, which form long minus chain structures under cosmic ray bombardment. Green originates from the fluorescent radiation of carbon-carbon molecules, which emit light at specific wavelengths when excited by sunlight. Blue hues correlate with ionized carbon monoxide and other ionized gases, reflecting distinct physical conditions across different regions of the coma. These color variations may reveal a layered internal structure, as surface material gradually volatilisces, exposing materials at progressively deeper depths. Each layer chronicles a distinct evolutionary history, where cosmic ray bombardment formed a complex organic shell on the surface, a process unfolding over millions of years, shaping the distinctive features we observe today. This radiation minus processed layer acts as a protective shell, shielding the primitive volatile materials within. As it continues its approach toward the Sun, it faces its most severe test. The perihelion passage marks the closest point in a comet's orbit to the Sun. Here solar radiation intensity reaches its peak. For this interstellar visitor, perihelion occurs at approximately 1.36 astronomical units. This position lies between the orbits of Earth and Mars. At this distance, the Sun's heating effect is sufficient to trigger intense physicochemical changes. Observational data show its brightness increases dramatically near perihelion, surging from magnitude 12 to magnitude 9, a roughly 15-fold increase in luminosity. This dramatic brightening is accompanied by massive gas release, expanding the coma's diameter to over 100,000 kilometers. The comet's tail develops complex structures. High-resolution images reveal multiple independent jets, ejected from distinct locations on the nucleus's surface. These jets likely originate from sublimation of ice in specific surface regions, forming directed outflows akin to rocket engines. Thermal stresses cause the surface shell to fracture, exposing underlying unprocessed material. The newly exposed ice immediately begins sublimating, producing fresh, gaseous components, including detected ammonia molecular derivatives. This offers a unique opportunity to study its internal composition. At the critical moment of perihelion, the object briefly vanished into the Sun's glare. Astronomers worldwide waited anxiously for its reappearance. When it re-emerged within telescopic view, researchers breathed a sigh of relief. Observations confirmed the nucleus remained intact, without fracturing as some models predicted. This finding indicates the object possesses considerable structural integrity, likely due to its thick, radiation-hardened shell. This shell acts as protective armor. Survival did not come without change. Observations reveal a marked alteration in its rotational state. Surface activity patterns also underwent significant adjustment. New gas jets became active, while some older jets gradually weakened. Orbital mechanics experts noted a subtle yet definite deviation between its actual trajectory and the path predicted by pure gravitational models. This deviation likely stems from non-minus gravitational effects, namely the recoil force generated by gas ejection. This phenomenon is quite common among comets in the solar system, especially when gas is ejected asymmetrically from the nucleus surface, producing a net thrust that alters the orbital parameters of the celestial body. Professor Loeb pointed out that if gas ejection exhibits specific directionally untiming, it could theoretically produce significant orbital changes. However, he cautiously emphasized that this still falls within the realm of natural processes, without requiring the introduction of artificial control hypotheses. This interstellar visitor is now receding from the Sun and returning to interstellar space along a hyperbolic trajectory. It currently lies beyond Mars' orbit and is departing the inner solar system at approximately 40 kilometers per second. Over the coming months, it will continue to dim until it ultimately falls beyond the detection capabilities of most ground-based telescopes. For amateur astronomers, opportunities for observation remain in the next few weeks. Using telescopes with apertures between 80 and 150 millimeters, under conditions free from light pollution, one may attempt to locate this faint, diffuse patch of light in the eastern sky before dawn. Though it will not display a spectacular comet tail, the knowledge that you are observing a visitor from another star system carries profound scientific and philosophical significance in itself. Regarding the nature of this interstellar object, the scientific community is forming a clear consensus. All reliable observation and evidence supports the natural comet hypothesis. Its chemical composition and physical properties, though exhibiting anomalies in certain aspects, can be reasonably explained within known astrophysical frameworks. Professor Loeb's dissenting view, while not widely endorsed by the scientific mainstream, has indeed spurred deeper data analysis and driven more rigorous theoretical testing. In the course of scientific progress, such unconventional thinking often serves as a vital catalyst. This discovery significantly elevates our detection capabilities. Next-generation wide-field survey telescopes, such as the soon-to-operate Avie Loeb Observatory, are expected to uncover more such interstellar visitors, potentially detecting several annually. This will inaugurate an entirely new field of research, interstellar astrophysics. By studying these samples from diverse stellar systems, we can compare their physical and chemical properties, and thereby infer the formation and evolutionary patterns of planetary systems within the Milky Way. Each interstellar object resembles a cosmic information capsule, carrying the formation history of its home star system. As it traverses the Milky Way, scientists estimate that trillions of such interstellar objects may exist near our solar system alone. They transport material between stellar systems, potentially including organic molecules and precursors to life. This interstellar material exchange may be disseminating the seeds of life across the cosmos. As we gaze upon this interstellar visitor gradually fading from view, we cannot help but contemplate our place in the universe. Earth is not an isolated island, nor is the solar system a fortress cut off from the world. Through countless such interstellar messengers, we are connected to the vast expanse of the Milky Way. They bear witness to the birth and death of stars, the formation and dissolution of planetary systems, and the cosmic minor-scale cycling and regeneration of matter. The arrival of this interstellar visitor not only provides invaluable scientific data, but also rekindles our awe for the mysteries of the cosmos. As it vanishes beyond our observational horizon, the scientific questions and philosophical reflections it leaves behind will continue to inspire humanity's courage to explore the unknown. In the endless cosmic voyage, this may be just one of countless interstellar encounters, yet for us, it represents a significant expansion of humanity's cognitive frontiers. It reminds us that countless mysteries in the cosmos remain to be unveiled. Its journey continues toward new stellar systems, carrying faint traces from our solar system as it persists in its eternal drift through the Milky Way. Meanwhile, we continue to gaze at the night sky, awaiting the arrival of the next interstellar messenger.